Introduction to Acids and Bases Part 2. We're going to look at a few acid-base calculations, how to calculate Kw, pH, the hydronium ion or hydrogen ion, and the hydroxyl ion. Also, pOH will be calculated here. Self-ionization of water is the first thing we need to understand to get at these calculations. Water is a molecular compound, but it does dissociate to a very small extent into hydrogen ions and hydroxyl ions. The equilibrium position is far to the left. At equilibrium at 25 degrees Celsius, the hydrogen ion concentration is 10 to the minus 7th molar, and the hydroxyl ion concentration is also 10 to the minus 7th molar. And so if we multiply those two together, we get 10 to the minus 14th, which means the equilibrium position is far to the left. So we still consider water to be a non-electrolyte molecular compound, even though it does dissociate to a very small extent. We can write this reaction with a single water molecule, in which case you get a hydrogen ion and a hydroxyl ion, or we can write it with two water molecules, in which case we get a hydronium ion and a hydroxyl ion. For our purposes, we will pretty much treat these two ions as the same, so that is something that you want to keep in mind. For your reminder for equilibrium, if I have a system in equilibrium, then I can write an equilibrium constant, and it's always products over reactants. So we have B cubed over A squared, and that will give us the equilibrium constant here. So if I want to take the equilibrium expression for water, it is going to be the products over the reactants, but now the reactant's a pure liquid, and so it will not show up in the expression. And so the ion product constant is just the product of the ions that make up water, and we could have the hydronium ion concentration times the hydroxide ion concentration, or we can have the hydrogen ion times the hydroxyl, really depend on how you write the equation, and so on. Kw at 25 degrees Celsius is always 1 times 10 to the minus 14th molar. That's a number that you will need to be familiar with. Sample Kw problem, if I ask you what is the hydrogen ion concentration in the solution in which the hydroxyl is 1.2 times 10 to the minus 4th, again, here is our equation for Kw, and to get the hydrogen ion by itself, we have to divide both sides by the hydroxyl ion concentration. So that gives us the hydrogen ion equals the Kw divided by the hydroxyl ion, or 1 times 10 to the minus 14th divided by 1.2 times 10 to the minus 4th. And so this will be the concentration of the hydrogen ion. So pretty simple equation, takes the form of A equals B times C. A is a constant, so if I want to solve for B, then I have to divide A by C. If I want to solve for C, I have to divide A by B. A measure of the acidity of a solution is called pH, something I'm sure that you have heard of. pH is defined as the negative log of the hydronium ion concentration. Again, we will treat that the same as the hydrogen ion concentration. The converse of that equation is the hydronium or hydrogen ion equals 10 to the negative pH. And just a reminder on the pH scale, 0 to 7 are acids, 7 is considered neutral. Anything that is greater than 7 is considered to be basic on the pH scale. So if I ask you what is the pH of a solution in which the hydrogen ion concentration is 1.2 times 10 to the minus 12th molar, you need to know that the pH is the negative log of the hydrogen ion. And so you just have to hit the negative sign on your calculator, find the log base 10, and then type in the concentration of the hydrogen ion, and that'll give you the answer. In this case, it's going to come out to 11.92, which indicates a basic solution since the pH is greater than 7. The converse of that equation, what is the hydronium or hydrogen ion given the pH of 8.56? You need to remember that the hydronium ion is 10 to the negative pH, and so since the 8.56 is the pH, we just have to substitute that in. Hydronium ion equals 10 to the negative pH, 10 to the negative 8.56, which gives us 2.75 times 10 to the minus 9th. To help you understand what logarithms are, the log, and don't confuse this with the natural log. We don't want the natural log, that's a button you'll see on your calculator. We want the log base 10, which is spelled that way. The definition of a log is the number to which 10 must be raised to get that number. So if we think of the number 1, we must raise 10 to the 0 power to get that. And so the log is 0. That is the number to which we must raise 10 to get the number 1. And the pH is simply the negative of the log. Since there is no negative 0, we will just call that 0. 0.1 is a tenth, or it equals 10 to the minus 1. And therefore the log is a negative 1. Again, it's the number to which 10 must be raised to get that number. And the log is going to be the negative 1 or 1. If we have 0.01, a hundredth of a molar concentration, that will be 10 to the minus 2. The log is going to be a minus 2, and the pH is going to be 2. And so by now you should see the really very simple pattern here. And one thing I want you to notice, as the concentration of the hydronium ion gets smaller and smaller, each one by a factor of 10, the pH is increasing by 1, so it's a logarithmic, not a linear scale. As you go from pH of 1 to a 2, it is 10 times weaker. If you go from 1 to 3, it's 100 times weaker. If you go 1 to 4, it's 1,000 times weaker. And so on the pH scale, a 2 and a 3 may seem only slightly different, but really there's a factor of 10 there. And again, 0 is the strongest acid, the most concentrated acid, the largest concentration. And as you go down, it gets weaker and weaker and weaker. At a pH of 7, we call it neutral. Neutral, again, not because there's not any hydrogen ions, is that both the hydrogen ion and the hydroxyl ion are both 10 to the minus 7th molar in pure water at 25 degrees Celsius. To help you out practice this, again, we have to do the negative log. If you understand logarithms, then 1 times 10 to the minus 1, that is the number which 10 must be raised to get that number. That is the number to which 10 must be raised to. And so those are just going to be 1, 4, and 12. If you get a number like 0.062, you just have to do negative log 0.062 on your calculator. That will give you a pH of 1.21. So it'd be a good idea for you to practice this as I do this. So maybe you want to hit pause and do these. If you have a hydrogen ion concentration of 2.24 and you do negative log of that, you actually get a negative value. So you can have negative values on the pH scale. If you have a number like this, be sure you put it in parentheses. To get the correct answer, you want to take the negative log of that entire number, and that will give you 12.49. Out of all of these, the pH of 12 indicates a basic solution, and 12.49 indicates a basic solution. All the rest of those are below 7 or they're acids. This would be the strongest acid having the lowest value. Given that Kw is the product of the hydrogen times the hydroxyl, and Kw always has a value of 1 times 10 to the minus 14th, at least at 25 degrees Celsius, the negative log of the hydrogen ion is pH. Negative log of the hydroxyl is the POH. And so if I take the negative log of this side, I must take the negative log of this side, which yields this equation, pKw, negative log of Kw equals the negative log of the hydrogen plus the negative log of the POH. Again, this is a logarithm, 10 to the minus 7th times 10 to the minus 7th equals 10 to the minus 14th. And so when you multiply exponents, you add them. These represent exponents, so we add them. And therefore, 14, which is the negative log of the Kw, equals pH plus POH. And so if the pH is 7, the POH must be 7. If the pH was 6.5, the POH must be 7.5. They must add up to 14. So a simple equation here, if the pH of a solution is 6.5, what is the pOH of the solution? The answer is just subtract from 14. And so 14 minus the pOH equals the pH. And for the second one here, if the pOH of a solution is 3.70, what is the pH and the hydrogen ion concentration? The pH is going to equal 14 minus the pOH, or 10.3. So that is going to be the pH. And then the hydrogen ion concentration, again, equals 10 to the negative pH. So we have to do 10 to the negative 10.30. That's going to come out to 5.0 times 10 to the minus 11th. I show you this because this is a question that you'll see, and it's going to involve two equations. From the pOH, you can get the pH, and then from the pH, you can get the hydrogen ion concentration. So it will take you two equations to get there. Last couple of details. This first question, neutral solutions lack hydrogen ions. That is going to be false. Neutral solutions have 10 to the minus 7th molar concentration of hydrogen ions. That is why the pH is 7. And the reason it's neutral because the hydroxyl ions also have a concentration of 10 to the minus 7th molar. Next one, as the hydrogen ion increases, the hydroxyl ion decreases. That is true. These two are dependent on each other. Remember, the ion product constant is Kw. This is a constant. And so if one of these increases, the other one must decrease. If when you multiply them, you always get the same number. In acidic solutions, the hydrogen ion concentration is greater than the hydroxide. That is true. In basic solutions, it would be the opposite. The hydroxyl would be greater than the hydrogen. And in neutral solutions, those two are equal to each other. Last question here, hydrogen ions are protons. That is true. If you think of the periodic table information, hydrogen has an atomic number 1, a mass of 1, so it has 1 proton in the nucleus and 1 electron. And if it becomes an ion, a positively charged ion, it has to lose that electron. So if we take that electron away, you are left with nothing but a proton. And that is the end of this lesson.